In 2.2, we're going to spend a little bit more time with linear functions. So we'll talk about linear functions in the context of a constant rate of change. Recall that in chapter 1 we talked about a linear model where we said y was equal to this capital A plus bx, and we built linear models from data. Now we're going to make it a little bit more general, and we're going to use the form that is more commonly used to represent a linear function, which is y equals mx plus b. So just so that you don't get too overwhelmed by that idea, these are the same function. They're exactly the same. We just are choosing different names for things, and most of the time you see y equals mx plus b. A is going to be little b. Capital A goes to little b. It's just being replaced. You're just calling it something different. Capital B is turning into m. Again, it's just being called something different. The function, the form, they're exactly the same. We're just changing the variable name, effectively, which isn't a variable. It's usually a constant, but we're changing the name that's being used for those things. So m is still your rate, and b is still just an additive constant. So, your m value, we would define, like cost per pound of apples. That is a rate. Whereas b, for example, like when we were renting the bicycle earlier, that dollar fee for just renting it, that was the fee that you always paid. That's going to be the same here. Something that is particularly unique about lines is that the average rate of change is going to be constant for a line. It is always going to be the same for any data set that you take for a linear function. So that value for the average rate of change is also the value for m, which we will call slope soon. If I give you an example of a line, so f of x is 3x minus 2, you can look at your average rate of change from x equals 0 to x equals 1. And so, we take f of 1 minus f of 0 over 1 minus 0, right? F of b minus f of a over b minus a. And that gets us, if we substitute in our function values, f of 1 is 1, f of 0 is a negative 2, 1 minus a negative 2 becomes a 1 plus 2, all over 1, getting us an average rate of change of 3. And from x equals 1 to x equals 2, just to try other values, see that they are in fact the same. F of 2, we have 4. F of 1, we have 1. 4 minus 1 gets us a 3 over 1. Again, we have 3 for our average rate of change. Now, I have generalized it, If we picked any values, so say x equals a and x equals c. I didn't use b because b is part of the form of the equation. I didn't want it to be confusing. So a and c. F of c minus f of a over c minus a. So if I plug c into the equation of 3 times x minus 2, so that becomes 3 times c minus 2, and then I subtract f of a, 3 times a minus 2, all over the difference c minus a, then I can simplify this. 3c minus 2 minus a 3a minus 2, so minus a minus, I have a minus 2 plus a 2, they cancel, These guys are going to cancel. Leaving me with 3c minus 3a over c minus a. And I can pull the 3 out in front, 3 times the quantity, c minus a, all divided by c minus a. Those guys cancel, leaving me with an average rate of change of 3, regardless of what my data points are. So you can see explicitly that for a line, my average rate of change is equal to that value that's in front of the x here, that 3 for this particular equation, which in general is m. And so if m is equal to 3 in the y equals mx plus b, my average rate of change is just that constant that's in front of my x, the 3 in this case. The other term, the b, is known as the initial value. It's the value of y when x is equal to 0. So if we look at the same function, the same linear function we just used, f of 0 is negative 2, We calculated that earlier. Negative 2 is equal to b, The equation is y equals mx plus b, or y equals 3x minus 2. So the plus b must be plus a negative 2 in order for it to be of the form mx plus b. We can apply this to an example if we look at the linear function of a flower's growth from seedling, so say that's about an inch, to full height, say that's 8 inches, over the course of 2 weeks. If it takes 2 weeks for it to go from 1 inch to 8 inches, let's determine the linear function for its growth. So first we have to determine, well, what is the rate at which it is growing? So if we're going to measure this in inches and in weeks, then the rate, right, we use our average rate of change. So we have 8 inches minus 1 inch over the course of 2 weeks that have occurred. So 2 weeks minus 0 weeks, right, the start. And so that will give us 7 inches over the course of 2 weeks in terms of the rate. So if this is the rate, then that corresponds to our m, right? That will be the m in our y equals mx plus b form. The b comes from the initial value. What was the value of its height when it started? That was 1 inch. That is going to become our b in the equation. So the linear function that models this growth is going to look like y is equal to 7 over 2x plus 1. Note that this is in inches, and this is the number of inches per week overall. Okay? Let's take a minute to graph this linear function. So if I'm looking at the height, so 0, 1, 1 is going to be 7 halves plus 1, so I'll end up with 9 halves. 2, I end up with 14, 15, 16 halves. And then 3, let's see, that becomes 23 over 2. If I graph this guy, what I'm going to find is I can look at slope as rise over run. That's the goal here. So let me graph this real quick and come back. Okay, so I sketched in the axes and put in through the first 3 data points. So 0, 1 to 1, 4.5, and then 2, 8. So this line, if I connect these guys, I can then approximate slope as rise over run. And with rise over run, I'll do a light green, dot, 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 down, and over. I can see that from 1 to 8, this distance is 7. And from 0 to 2, this distance is 2. So rise is 7 and run is 2. So slope equal to rise over run, as we consider it, in this case, would be 7 over 2, which is the number that we computed anyway, and that we used when we plotted it. But here, you can actually see it. Okay? Please let me know if you have any questions. See you in class.